Alright, so this video is a continuation of the video that we had for homework where we were talking about how to analyze a function. And there were two more characteristics of graphs that I wanted to go over. And they're fairly similar, so I went over them in class and the video didn't work. So I'm going to go ahead and do them now. So the first characteristic that I'm asking you to add to your last set of notes is symmetry, how we look for symmetry. And there are three different types of symmetry that we look for. And some graphs will have one type of symmetry, some graphs will have more than one type of symmetry, and some graphs will not have any of these types of symmetry. So it is possible for you to check for symmetry and end up concluding that there is no symmetry. So the first type of symmetry that we'll look for is symmetry to the y-axis. So that means that you can fold the graph over the y-axis and see that it's the same on each side. The other type of symmetry we'll check for is symmetry to the x-axis. And then the last type of symmetry we'll check is symmetry to the origin. And symmetry to the origin is not like folding a sheet of paper. Symmetry to the origin is like if you were to take your pencil and put it right on this point, then you could spin around your pencil, and when you shift this upside down or spin it 180 degrees, it looks like the same graph. So that's what we mean when we say symmetry to the origin. All right, so for each of these different types of symmetry, you have to do a different test. So to check for symmetry to the y-axis, we're going to plug in negative x. To check symmetry to the x-axis, we're going to plug in negative y. And to check symmetry to the origin, we're going to plug in negative x and negative y at the same time. So three different ways of checking it, but the conclusion that you get is based on the same type of result. So after you plug that in, you're going to simplify what you have. So if you have negative x to the fourth power, you're going to say negative x times negative x times negative x times negative x would give me a positive x to the fourth. Or if you have the absolute value of negative x, then you'd say anything inside absolute value is positive. So it'd be positive absolute value of x, that sort of thing. So you would simplify it. And then after you simplify, if you get back to the original equation, then the equation has that symmetry. So you plug in the value that you're supposed to plug in and simplify, and if you get back to the original equation, your graph has that symmetry. So I just want to show you based on these three pictures that we wrote. So the first picture we had was a parabola, y equals x squared. And when we check for symmetry to the y-axis, we plug in a negative x. So I would say y equals negative x squared. And when I simplify that, I get y equals negative x times negative x is positive x squared. So you can see that after I simplified, my original function and my resulting function were the same. And so that confirms, yes, it is symmetric to the y-axis. If I do the same thing for the next graph, this is a sideways parabola, so it is x equals y squared. So if I plug in negative y, I get x equals negative y squared. And if I simplify that result, I get x equals negative y times negative y, which is positive y squared. So again, my original function and my resulting function, well, these are not functions, but they're the same. So if you guys recall, the reason I'm saying this isn't a function is because we learned earlier on in math that it has to pass the pencil test or the vertical line test. And since this equation touches two parts of my pencil at the same time, that means it's technically not a function. So I really should be referring to it as an equation, but most of the time we do deal with functions. Okay, so this one, regardless of whether or not it's a function, it is symmetric to the x-axis. All right, and then last we're going to try the origin. So the original equation that I graphed was y equals 1 over x. And so if I go ahead and plug in negative y and negative x at the same time, then that gives me negative y equals 1 over negative x. And for me to simplify this, I'm just going to go ahead and divide this negative over to the other side. So negative y divided by a negative is just y. The fraction 1 over x with the negative sign in the front, if I divide it by a negative, then the two signs cancel and I just get 1 over x. So you can see that that resulted in the original equation. So these are very simple examples. We're going to deal with functions and equations that are a little bit more complicated, but the idea is the same. So I'm going to go through 2 examples so that you can see them. And when we do the problems, we are going to take them through all 3 tests, right? So we're not just going to isolate one test. We're going to check for all 3 typically. So to check to see if it's symmetric to the y-axis, that means that I plug in a negative x. So I'm going to say y equals the absolute value of 2 times negative x. And when I multiply 2 times negative x, I get negative 2x inside of the absolute value. But no matter what I plug in the absolute value, it's always going to become the positive result. And so I'm going to say that if I take the absolute value of 2x, that's basically taking, if I take the absolute value of negative 2x, that's basically taking the absolute value of 2x. All right, so I got rid of that negative sign because absolute values always make things positive. And so that means that our resulting equation is the same as our original. And so this function does have symmetry to the y-axis. For me to check the x-axis, I'm going to plug in a negative for y. So I get negative y equals the absolute value of 2x. And when I simplify that, I just want my y to be by itself because the original equation had the y by itself. So I'm going to divide the negative over to the other side, and that would give me y equals negative of the absolute value of 2x, and that is not the same as the original, and so I'm going to say that that is not symmetric to the x-axis. And then for my last test, I'm going to plug in a negative y and a negative x at the same time. And so this gives me negative y equals the absolute value of 2x. And then I can go ahead and divide the negative over to the other side, and I get y equals the negative absolute value of 2x. And so again, my conclusion would be it is not symmetric to the origin. So we would say this one is only symmetric to the y-axis, but it does have symmetry. All right, we're going to do another example. I'll flip the page so I have space. Okay, so for this example, we're going to do f of x equals 2x to the 1/3 minus x. So with this one, it has the f of x, that function notation. I don't like to have f of x in problems where I'm plugging stuff in for y, so I'm going to go ahead and rewrite that as a y. And then I've got a 2, and here for me, I am not super comfortable in my brain thinking about rational exponents, and rational exponents just mean that you're talking about a radical of some sort, and so this radical would be a 3rd root, so I'm going to go ahead and rewrite it that way so it's easier for me to think about. Okay, so now I'm going to go ahead and do my 3 tests. So I have to test symmetry to the y-axis by plugging in negative x's, so 3rd root of negative x minus negative x. And if I simplify this, I have to think about what happens when I cube root a negative number. So square rooting negatives is not allowed, but cube rooting negatives is fine. If I take the cube root of negative 8, I get negative 2. So anytime you take the cube root of a negative, all it does is it brings the negative to the front, and you just have the negative version of that answer. So I'm going to say that when I start to simplify this, it's going to be negative 2 times the cube root of x, whatever the size of that number happened to be. And then when I minus a negative, I get plus. Minus minus makes a plus. So if I compare this to the original function, those are not the same, so this is not symmetric to the y-axis. Next, I'll go ahead and try symmetry to the x-axis. And I just have the negative in front of the y. So in an effort to make it look like the original, I'm going to go ahead and divide this negative over to the other side. And so what it does is it makes the y positive, but it changes the signs of both of these terms. So negative 2 cube root x plus x. And again, that's not the original, so it's not symmetric to the x-axis. And then last, I'll go ahead and check the origin, and so I'm plugging in a negative for y and a negative for x at the same time. And what you'll notice is that after you've done the y by itself and the x by itself, the origin feels a little bit repetitive. It doesn't mean we can ignore it, but it does mean that we can take some of the work we did before and just kind of rewrite it out again. So if I remember the work that I did before, I'm going to go ahead and leave my y negative for now. But if I remember the work I did before, I know that I moved the negative to the front. And I know that minus minus made a plus. And if I remember the work that I did for the second part, that means that I take this negative and I divide it over to the other side. So I'm going to have y. And then when I divide it over to the other side, it changes the signs of both of these terms. So that'd be 2 third root of x minus x. And now if I compare it back to the original, it's actually identical. And so that means that this particular equation was symmetric to the origin. Okay, so one last type of characteristic we'll look for is to determine whether functions are even or odd. And the nice thing about checking for even and odd is it's very similar to checking for symmetry, but it only involves one test, not three. So even functions are symmetric to the y-axis. And the most simple version of an even function would be like y equals x squared. So this right here is even. Odd functions are symmetric to the origin. And I drew a picture of y equals x to the third. It's not the most simple one that I could come up with, but I like that one. All right, so even, odd, symmetric to the y-axis, symmetric to the origin. So to check both of these, you only have to do one step, well, a couple steps, but the first step is the same for both. For both of these, you plug in negative x. All right, so that's why it's going to remind you of the symmetry test. For both of these, you plug in negative x. So for even functions, if you get the original function as a result, then you know that it's even. If you plug in negative x and you get the negative version of the original, then you know that the function was odd. So we have one test, but instead of it being true or not true, we say depending on the result, we have our conclusion. Now it's possible for you to plug in the negative x and simplify it and not get the original as an answer, and not get the negative version of the original as an answer, and then your conclusion would be that it's not just even or just odd, it's probably a combination of the two, and so that's a possibility as well. Okay, so we'll check to see if it's even, odd, or neither. I guess you could add this to your notes. Actually, neither. Okay, so we're going to go ahead and do a couple examples just to make sure that it makes sense before you have to practice for your homework. All right, so for this one, I'm going to take this function and I'm going to plug in negative x. So negative x to the fourth minus 2 times negative x squared plus 1. And so if I simplify this, I have negative x times negative x times negative x times negative x. And that gives me positive x to the fourth. And then I have minus 2 times, and then this is negative x times negative x, and so that gives me x squared, that's positive, and then I still have the plus 1. So if I look at this, I notice that when I plug in negative x and simplify it, it's exactly the same as the original, and so that means that this function is even. If it's exactly the same as the original, it's even. Okay. Odd functions are a little bit harder to recognize, and so I want to go over a specific example of that. We're going to do y equals negative 5x to the third plus 6x. So just like before, we're going to plug in a negative x. So here I have negative 5, and if I do negative x times negative x times negative x, I get a negative. So this is being multiplied by negative of x to the third. All right, and then 6 times negative x is just minus 6x. So if I keep simplifying that, I'm going to get y equals negative 5 times negative x to the third is positive 5x to the third minus 6x. And if I compare this to the original, I can see that they are not the same. And so that means that this graph is definitely not even. So now I'm going to go ahead and check to see if this graph is odd. And what I'll do is I'll put a negative sign in front of parentheses, and then I'll switch the signs of both of these. So I'm going to say negative 5x to the third plus 6x. So now when I do it, I have the negative version of an equation. And if I compare this, I can see that this right here is the original function. So this is the negative version of the original function, and that means that this is odd. So we have exactly the original function or the negative version of the original function.